Alright, let's start. So we discussed the house order reflector last time, and yeah, I was confused at the end of the last class that yeah, so to obtain the reflector matrix, so if we have x over here and then x ahead here, yeah, and then yeah, if we want to obtain this reflected point, and then starting, yeah, this is the starting point, and then yeah, so this guy is x hat minus x, right? And then yeah, we have to move twice the length of this original vector, so that's why we have 2 over here. But yeah, I was confused about the sign here, so it shouldn't be minus, but it should be added, right? Yeah, because from this starting point, so we are moving 2 times this vector from that starting point, so we have a plus sign over here. Okay, so in this case, it is not a 3x minus 2x hat, so instead it is minus x plus 2x hat. Okay, and then what was x hat? So it was, yeah, it was a projection of the original vector x onto the orthogonal complement, or the other space of S2 with respect to the V1, the vector V. So this is our complementary projector, right? So we understood this part, and then if we plug this into here, okay, and then we will obtain this equation. So, so does it make sense? Okay, so another maybe simpler explanation to derive this guy is, yeah, so if we start from x, and then suppose our vector v is, yeah, as seen here, v is like this. So in the case, so v is this guy, this vector, and then we just directly project this vector x onto this line v, and so in this case, so we are projecting x onto this part, right? Because this is the line that we are projecting the x onto, so we are considering the situation where we project x onto the line spanned by the given v, okay, and then we obtain the projected vector like this, and then this vector is, yeah, simply, yeah, we just normalize v into this form, okay. So this is the normalized vector v, and then how do you compute this projection? So once we normalized this vector, and then we simply inner product with this guy, with this, so that we can obtain the length of it. Okay, so in this case it is V transpose and X, and then the denominator is in this form, and then once we're obtaining this scalar vector or the length part, and then we can just simply multiply that vector, right? And so in this case, this guy becomes, yeah, square root of this length, and then this guy is, like, this guy is scalar and this guy is vector, and so we can move it to this part, right? So V transpose V, yeah, it should be the length of V okay, so the length squared is becoming, will become V transpose V, and then if V is moved here, V transpose and X, right? So again, this guy is the projection vector, okay, projection result onto the line spanned by V, right? So this guy is this part, right? So simply moving from X, starting from X, the reflection point with respect to this plane or hyperplane orthogonal to V is that we first obtain this part, which is this vector, and then we simply subtract this part twice from the vector X, because starting from X we just negate the vector and then move it, move it with respect to the twice of this vector. And so in this case, X minus 2 times V transpose V and V transpose X, right? So in this case, if we factor it out, and then it will become I minus 2 times V transpose V, V transpose, and X. Okay, so this is another simpler way to obtain this reflection matrix. Okay, so using this reflection matrix, we apply or utilize this to obtain the QR decomposition of a given matrix. And so here the main idea is we carefully, let's see. Yep. So given an arbitrary vector X, and this vector is so if we are given three column vectors in our original matrix, and then when doing the QR decomposition, and then we need to compute this orthogonal matrix Q and upper triangular matrix R, right? So in this case, this is our matrix A, and then if we just multiply Q transpose on the left, then this part is gone. Then we need to obtain this matrix R, which is an upper triangular, by multiplying the orthogonal matrix on the left, or the transpose of an orthogonal matrix. But if Q is orthogonal, and then Q transpose is also orthogonal. So in this case, if we compare this matrix A and the matrix R, and then the first column of the matrix R is this kind of vector, right? The first element is non-zero, and then the rest of them is 0. Okay, and then by multiplying this Q transpose with this first column vector that we originally have, we want to obtain the vector that has only the non-zero in the first dimension and all zero in the remaining the rest of the dimensions, right? So in this case, we want to perform this operation using this reflector matrix. So suppose this vector is 1, 2, 3, for example. Then let's imagine the reflection that reflects this guy onto into some vector that has only the non-zero in the first dimension. So in this case, so let's just simplify the two-dimensional case. So we have an original point here, right? And then after doing the reflection, the reflected point should be on the first axis, something like this, right? And so our reflection line will be something like this. So we need the reflected point over here, right? So let's first think of the length of this vector. So the original vector length is like this red line segment, and the reflected one will be also this guy. And then in general, the reflection will not change the length at all, right? Because we just reflected it onto with respect to the line or the hyperplane that that passes the origin. So in this case, the reflected point will have the same length. Okay, so in this case, how can we represent this vector? The first element is the only non-zero one, and then the remaining one is all zero. In this case, we can represent this vector into this form. In the case of 2D, it's 1, 0 times. Suppose this vector is x, and then what is the length of the reflected vector? So that reflected vector should have the same length, right? So this guy should be the resulting vector after reflection. And more specifically, all the elements are 0, and then the first element should be the length of the original vector, right? Okay, so in this case, the problem is how can we obtain our reflector matrix that is represented by I minus 2 times V transpose V and VV transpose, right? Okay, so in this case, this part, or so this part, so we already studied how we compute this component, right? What was the component corresponding to this guy? It was like minus 2 times V transpose V and VV transpose and X. Right? Because if we multiply X over here and then moving this X into this new point, the remaining part or the difference is represented in this form, right? Okay, so in this case, we can now represent we can now represent this vector v. And how can we obtain this vector v? So simply this vector v can be represented as the difference between the vector x and the resulting vector after the reflection. Okay. So how do you obtain this guy? So once we do the reflection, and then this is the input and this is an output vector, and simply just take the difference between these two vectors, and then at least that vector will be like parallel or at least scalar multiple of this orthogonal vector to our hyperplane, right? So if you imagine the reflection with respect to some hyperplane, that is, this hyperplane is orthogonal to some vector v, right? And then suppose we obtain, starting from the input vector x, and then obtain the output vector as maybe y, okay? And then if we take the difference between y and x, okay, and then this vector should have at least the same direction as this orthogonal vector or the normal vector v of our hyperplane, right? So our vector v, by definition, this vector v was the normal vector of our hyperplane, and then this vector v should have the same direction as this this guy minus this, right? Okay, and then does it need to have a unit norm or unit length? Yeah, actually it doesn't need to have the unit length, because we didn't assume any kind of unit vector property of this vector v, because in this part, vector v will be normalized through this process of normalizing their squared lengths, right? So we can simply, so here the conclusion is we can simply set our vector v as this guy, right? Okay, and then should we care about the direction of this vector? So should vector v be this guy, or should it be like x minus? Can we set v in this form? So which one is correct between these two? The answer is both of them are correct. So it doesn't matter. Which one we use, because in the case of a projection, the direction doesn't matter. So whether we set v as this guy, okay. So in this case, the projection will be like the projection of an x onto this line v is this guy, right? Okay, and so in this case, the inner product will have the length of this part, and then the direction will be our v. And then if our vector v is along this direction, okay, and then in this case, this unit vector, for example, like unit vector v and vector x will have now the negative sign of their inner product. So simply so this is one example of unit vector. And then suppose we want to project this guy onto the line spanned by this, okay, and then we just simply perform the inner product, right? And then So this one, yeah, this is the result of this projection onto this line. And then if we just use the negated vector, right, and then we also have a negation over here, so that way the inner product gets the negative sign over here, but this unit vector will also have the negative sign, and so they will cancel out, so the direction doesn't matter, right? And also intuitively, yeah, the line spanned by this vector or this vector should be the same. So projection of that onto that line, okay? So the projected point shouldn't change at all, okay? Okay, so in this case, yeah, whether V is set as this guy or this guy, so the result will be the same. So we have freedom to choose any direction between these two, right? Okay, so once we set our matrix F in this form, where the vector V is set as this guy, okay, and then we can obtain this reflector matrix that maps a given, currently given column vector into the vector that has only the non-zero in the first dimension. Okay, so for example, suppose you are given 1, 2, 3. Okay, so in this case, through our reflection, what should be the resulting vector? So the resulting vector should be 1, 0, 0 times. So this alpha should be obtained as 1 squared, 2 squared, and 3 squared, and square root of it, right? So at least we know this is our reflection vector, right? And then suppose this guy is A, and this guy as B, for example, and then we simply set V as P minus A, right? And then this this can be used as our vector V that forms this matrix, right? And then we now obtained this reflector matrix that maps this 1, 2, 3 onto this vector on the first axis. Okay. So once you obtained this matrix, okay, and then so why do we do so? Given, for example, the input matrix that has a 3 column, and then suppose we call this matrix as Q, maybe Q, and then we apply or multiply this Q on the left, and then at least this vector should have 1 squared, 2 squared, plus 3 squared, and 0, 0. Okay, so in this form, at least we became one step closer to this upper triangular matrix R, right? Okay, so in that way we handled or we took care of the first column. Okay, then now let's call this as Q1. Okay, and then now it's time to handle the second column. The second column, in order to compute handle the second column, and then we consider another matrix Q2 that actually transforms this part into also some alpha times 1 and 0, right? Then if this guy was maybe 4, 5, and then this alpha should be 4 squared and the 5 squared, right? And then we consider another reflection matrix that actually reflects this two-dimensional vector onto another vector along the first axis, right? So in this case, yeah, I want to point out that we don't actually consider, or we ignore the first dimension. Okay, so the first dimension, yeah, is ignored, but we only look at the remaining dimensions. So if we have a 10 dimension, then once we obtain the 10 dimensional vector that has only the non-zero in the first dimension, and then after multiplying this matrix Q1 on each of our columns, and then at least the first column will have this simple form, and then we have the remaining part after multiplying the second column and the third column with the same matrix Q. And then now we look at this second column, but we don't actually consider that, but we only consider this part. So the remaining, like a 9-dimensional vector, and then we apply, in this 9-dimensional vector, we apply another reflector matrix only on this 9-dimensional vector. And then how do we do so? So still this matrix Q2 is 10 by 10 matrix, right? So to handle this, we actually embed the smaller reflector matrix into this 10 by 10 matrix, and this is how. So for example, our Q2 is composed of this sub-blocks, or this block matrix. So it's like a 10 by 10, and then we have 1 by 1 as an identity matrix, and then over here we have 9 by 9 reflector matrix. Okay, so in this case, if we form the second matrix in this way, then see. For example, let's suppose I is 2 by 2, which will be corresponding to maybe the third step, or Q3, for example. Then maybe 4 by 4. So in total, it is like a 6 by 6 matrix. So it means that our column matrix, the column vectors, are in 6-dimensional, right? Okay, so in this case, we don't care about the first 2 dimension, and then we have 4 different numbers, but here, we want to make this guy into some non-zero 1 and 0, 0, 0, and also some new value, right? Okay, so in this case, if we compute the matrix multiplication with this and this column vector, okay, so just like performing the inner product with this guy and this guy, which produces this guy, so we can apply this perspective in a block, level. So in this case, we now have like a 2 gigantic row, or 2 row vector over here, the first row vector and second row vector, right? And then this first row vector times this guy, okay, that will produce this part that has the same number of rows, right? And then this second part, like this, and then that will be multiplied with the same part, and that will produce this part, right? So from that perspective, okay, so we have 0 over here and 0 over here. So I and 0 times this vector and this vector, and then it is producing the same vector for the first 2 dimension, right? And then this block, or this gigantic row times that vector will multiply this 0 part with this, and so those 2 first dimension will not be involved, and then this second this block of F will be multiplied this guy with this guy to produce this part, right? So if we embed this a smaller matrix like give me 1 second. Okay. So if we embed a smaller reflector matrix F into a larger matrix in this form of block diagonal matrix, where the first block is identity, and then in this case the first dimension corresponding to this identity matrix will not change at all, and then the second part will be only multiplied with this matrix F, and so we can form this matrix F by also using this reflector matrix that maps this guy onto here, right? So back to this simpler case. So if we obtain the 4 and 5, and then it will be obtained, it will be computed as this matrix after the reflection, and then in this case, if this matrix is C and D, for example, and then D minus C will be our new vector V. Okay. So by using this vector V prime, we obtain this I minus 2VV. Let's call it V2. Okay. Okay, so this is how we obtain the smaller matrix F in the second step that will be embedded into the larger, like 3 by 3 matrix or maybe 10 by 10 matrix of Q2. Any questions so far? 네. 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 그렇죠. 네. 맞아요. 그러니까 so how is it related to QRD composition? So once we do this iterative like upper triangularization that makes this a dense vector into the vector that has the non-zero at only at the first dimension. Okay, and then we will make 0, and the second vector we will make 0 over here, and so on, right? So that way we obtain the upper triangular matrix R, right? And then once we compute this Q1, Q2, and so on, okay? So this part, and then this part is basically our orthogonal matrix transpose. So if we just multiply this matrix transpose again on the left, and then this one will become identity, and then we will obtain the Q times R. So this entire product of these different Qs, where each of which is a reflector matrix. So the whole product of these will work as our Q transpose, because we need transpose of that to move it to the right. And also, so in this case, we have to also understand that this Q2 is actually applied to the first column, right? First column. So, the how we make this Q2 is to convert this second matrix into this form, right? We want to introduce 0 over here, right? So that's how we obtain Q2, and this Q2 is still multiplied with the entire matrix, right? So this Q2 should be multiplied with the first matrix, the first column, right? So in this case, we can easily see that this Q2 will not affect or will not change this first column at all, because in this case Q2 will be embedded into, for example, 3 by 3 matrix, and then this F part will be embedded into this lower right part, right? So in this case, suppose the first column, or it will be 0 time x and 0 and O0, and the second column will be x and 0 and things like that, right? So in this case, if we imagine the multiplication with this guy and this, okay, and then this identity matrix will be applied to this part. So this one will not change at all, and then now we compute this inner product with this sub matrix or sub row with that one, right? And then here in this case, the first block, so this part is 0, and so 0 times that part, like this, right? That will produce 0, right? And then f times this vector will also be 0, right? So in the upper part, this guy is 0. In the lower part, this vector has all 0, right? So it will not affect or change the first vector at all, right? So that's how we preserve or maintain this upper triangular structure on the previous columns. Any questions? Okay. And then now, let me just briefly discuss about this choice of reflector. Okay, so in this case, if we have maybe 1 and 2 as our original vector, and then we thought of the reflection vector that is on the first axis as this form. So 1, 0, and 1 squared, 2 squared, right? But what about another choice? I mean, is that the only solution for our reflection result? Actually, another answer exists as this form. So that answer is 1 times 1, 0 times this guy. Okay, so in this case, we start from this vector, and then we choose another vector that has the negative sign on the first dimension. Okay, and then all the rest of the vectors should have 0. So in this case, geometrically, we can also think of the reflection. So in that reflection, the hyperplane is defined in this form, not this guy, right? So this is certainly possible. So in this case, so this is our A, and this is our B, for example. And so initially we considered V as B minus A, but in this case, it can also be represented as A minus B, right? Because the direction doesn't matter when performing this projection, right? Okay, so in this case, we can represent X plus minus and E1, where E1 is this kind of vector, right? Okay, so which one will we choose? Plus sign or minus sign? So in this slide, the better choice will be to select the sign. So let me just give an example. So if our vector is 1, 2, so in this case, we just change it into this form, and we just choose a plus sign as the result of the reflection. And suppose we have this guy, -1 and 2, or -1 and 2, and in this case still the reflection point will have these two possible choices, right? But in this case we have a negative sign on the first dimension, and so we follow, or we just select that sign, and we just make this sign as -1. So yeah. Oh. Yep. Okay. So yeah, let me just give some intuition about this choice. So so I was I kind of explained a little bit confusingly. So so let me just let me just fix some of the explanation. So if we have a plus sign over here, and then the resulting reflection should be the negative sign, should have the negative sign. And then if we have a negative sign over here, and then in this form of a minus b, which is the original vector x and minus, and then plus minus e1, right? So in this case, if we take the plus sign over here, and then it will have the minus here, and so this guy is our reflection result, right? So intuitively, if we have an x that has the positive sign in the first dimension originally, and then our reflection point is chosen as this point. Okay, so in this case, our vector v is x plus this guy, right? So we actually select the projection, the reflection point that has a different sign in terms of the first dimension. And why is it so? Why is it so? So the reason is, like reflecting this guy onto this guy that has the same sign, and in this case our vector v is represented as this guy, right? And if we choose the reflection point that has a different sign in the first dimension, and then our vector v is vector v has this guy, right? So the reason for choosing this guy is because in terms of the direction, in terms of the direction, this scenario can have a higher probability of more exactly representing that direction. So that means, so if we consider some numerical error or finite precision kind of computation, or floating point computation, and then suppose we are given x over here, and then in this part, this normal, this length part was computed a little bit approximately. For example, as we saw in the previous lecture, suppose our vector is 1 and for example epsilon, where epsilon is really small. Okay, so in this case, ideally this the norm should be computed into as this form. But if epsilon is really small, so it is, if it is smaller than 10 to the negative 16, and in this case we will not be able to compute this length exactly, right? So now a little bit of an error is involved. And so in this case, what's the actual effect? So even though this guy should have been like this, and due to our approximated computation, it was just computed as 1, right? So instead of using this point, we are actually computing this point as slightly smaller vector like this. So in this case, the direction will be computed in this form, which has a little bit of an error in this form, right? Okay, so in this scenario, let's consider the angle over here. I mean, the amount of this angle is the amount of an error that we have to introduce due to this inaccurate or approximate computation. So in this case, let's think of the same scenario in this part. So over here, instead of using this, we are using this, right? And so in this case, between these two vectors, the angle difference is corresponding to this part, right? So the point is, we want to map or reflect that point to like relatively farther point, right? So that's the idea of changing the sign. Okay, so in that case, if the distance between these two, then the length difference is not that much. So likely the error might be relatively small. I mean, the introduced error might be smaller than this case. Okay, so this is the main idea. Any questions so far? Okay. So overall, we choose this negative sign over here, right? And then the negative sign means another negative sign, and so we obtain the plus sign, and then the result, resulting V is represented in this form, right? Okay, so this is the pseudocode of this Householder QR decomposition. And also, by the way, this reflection that maps the vector into another vector that has only the non-zero in the first dimension. That is called this Householder reflection or reflector. And so in this case, using this Householder reflection, the QR decomposition is computed in this form. So we iterate through the first and until the last column of the original matrix. Okay, so we have n different columns, and then we process each column one by one. Okay, then our vector, vector x is like, initially we will choose the entire vector in the case of first column, and then we form our v, right? And then first we just normalize this vector v, okay? And then now once we normalize this vector, and then when computing this guy, I minus 2 times v transpose v and v transpose, okay? So this part will no longer be computed, right? And so this part, times this vector, the first vector. So so that way, we will just change it into this vector, right? But that's not the end. When multiplying this guy with this column, first column, we need to compute the multiplication with that same matrix with the remaining or the rest of the other columns, right? Okay, so in this case, we just simply bring this second column, and then we just multiply this guy, right? And so on, right? So that is the first cycle or the first iteration, and then moving on to the second iteration, and then suppose this guy was changed into this form. So this is the result after the first iteration, and then we embed our reflector matrix onto to be applied this part, right? And so using this guy, right? So that guy is selected as this guy for k being k equal to 2, and then so we start from 2 to the remaining dimension. So this is 2 to m, right? And then we are at the second column, right? So this is that solve vector that we handle at this moment, and then we form this guy, okay? And then where is the this kind of embedding part of this submatrix of I on the first block diagonal part and the second diagonal part as our reflector matrix. We don't actually see that explicit formation of our matrix Q, right? So in this case, we just compute the matrix R, and in that case, we know that, in this case, our block diagonal matrix and then multiplication, I mean, this is an identity matrix that will be multiplied with the upper part. So we don't actually need to compute that, right? And so we only need to compute the matrix multiplication with F and this part, right? So that way we involve this kind of submatrix, right? So k comma k, or 2 comma 2, and then the remaining submatrix. Okay, so that is this part. So I times this guy will be this guy, and then that guy is the result of multiplication with this, right? So this is how we perform this house order QR factorization. So once we finish this computation, then our matrix A will now change to the upper triangular matrix. So that way we obtained R, right? Then where is Q then? So in this particular pseudocode, we don't actually maintain our Q. So in this particular form, we don't store, or we don't explicitly obtain the matrix Q, but we only compute R. Okay. So why don't we need to compute this explicit matrix Q? So there are like many many applications or many scenarios where we don't actually need to compute this this Q. Okay, so let's think of, for example, like a least squares problem. So this is our least square problem. So A is, for example, like this. So we have a five equations, and the variable we only have 3 variables. So this is the one example of this least squares. And then here we can apply the QR decomposition to solve this guy. Okay, so how we solve it is as follows. So suppose we have a QR decomposition of matrix A. Okay, so in this case, I want to claim that this guy is okay. So the main difference between the left and the right part is I just I just multiply the Q transpose on the left over here, right? And so between these two, the solution are the same. Okay, and why is the solution be the same? Okay, so let me just start with this guy, ax minus b, and we consider its norm, right? And then, yeah, typically we consider this a squared form in order to avoid this computation of unnecessary, square root value. And so in this case, yeah, we know that, yeah, we know this relationship, and so b minus ax minus b transpose and ax minus b, right? Okay, and then let's consider this guy, or this guy. Okay, so in this case, Q transpose ax minus b and transpose and Q transpose ax minus b, right? I just applied this formula, and then this guy is ax minus b transpose and Q transpose being equal to Q, right? And here we have Q transpose ax minus b, right? And so in the case of orthogonal matrix Q, which is the square matrix and having orthonormal columns, then we know Q transpose Q is Q transpose is an identity matrix, and so this guy is identity matrix, and so this guy is actually equal to this guy. Okay, and also this guy is always true with regardless of any vector x, right? So in that sense, it is 항등식이죠, 항등식. So it is true, regardless of any vector x, right? So the vector x that minimizes this guy will actually minimize this guy because those two are exactly equivalent. Okay, so solving this is equivalent to solving this, and if A is having the QR decomposition, and once we multiply Q transpose on the left, Q transpose QR x minus Q transpose B, and this guy is, so this guy is now Rx minus B. Okay. Okay, so utilizing this QR decomposition and multiplying this Q transpose on the left into this original least squares problem, that will make the same problem into this form, and then solving this form will be much easier than the original form, because this matrix R is upper triangular matrix. And so let's just exploit or take advantage of this upper triangular structure to solve this least square problem. Okay, so we are assuming this 5x3 matrix, and then once we compute the QR decomposition, and this R matrix should have the same size as matrix A, and it is upper triangular matrix, and thus yeah, the R will have this form, right? Oops, sorry. Well, we need a Q transpose over here, right? Okay, so this X mark is indicating non-zero vector, and then yeah, we have to compute this vector X, which is our variable, and Q transpose B is in general like full vector, like all non-zero vector. Yes, some non-zero one. Okay. Okay, so in this case, this guy, yeah, will produce like still 5-dimensional vector, and then what is the last 2 dimensions? What is the last 2 values? So it should be 0, because in this case it will produce 0 and then also produce 0, right? Okay, and then if we compare or take the difference between this vector and this vector, which is our Q transpose B, right? And then we want to minimize these 2 vectors, or the difference between these 2 vectors, right? And then the last 2 dimensions, yeah, they will remain as 0, regardless of any particular variable values, right? So we have we can do nothing to minimize the difference between this 0 vector and the given vector over here. So yeah, for example, as a result of this Q transpose B, suppose we obtained maybe 1, 2, 3, 4, 5. Okay, so in this case, yeah, we can say that the minimum amount of an error, minimum amount of an error will be 4 squared plus 5 squared, right? Because here we have 0, and this guy has a 4 and 5, and then taking the difference and then considering the L2 norm, and then 4 squared and 5 squared, that will contribute or add it to our total error, or the L2 distance between these two, right? So we can say that the L2 distance, squared L2 distance, should be at least greater than or equal to 4 squared plus 5 squared, right? And then now it's time to consider the first 3 dimensions, where we can have some freedom, or we can have some controllability of the first 3 values. So in this case, yeah, in general, the upper part we can achieve zero errors. So it is like 1, 2, 3, 4, 5, 6, and then we want to multiply this upper triangular matrix and this guy, and then make it as close as possible to 1, 2, 3, which is the given vector, right? And so if it is so in this case, we do the back. I forgot the name. It is back, forward. Yeah, it's the forward pass and the backward pass. So it is also used in the LU decomposition. But so each of these equations should be the same as 1, 2, 3. And the last one is involving only a single variable, and 6 times this star should be equal to 3, right? So star should be 1/2, right? And then we just plug this 1/2 into this guy, and then 5/2, and then subtract it from this 2, and then we can obtain the second star, and so on, right? Right. So it is called the back substitution, right? Back substitution, because we start from the back, and then we substitute each of these variables that we obtain into upper equations. But at least in this form, we can simply obtain the optimal solution for this star values, right? And then in general, if we have this upper triangular matrix where we have non-zero ones along the diagonal, then it is a full rank matrix of square matrix, 3 by 3, and then we have 3 equations and 3 unknowns. So in general, we can solve or perfectly satisfy all the equations using the same number of variables. And so the upper part will be, in general, will have zero errors. Okay, so as I mentioned, the error should be at least that part, but that is our actual minimum error that we can achieve. So in this form, if we obtain this QR decomposition and then change this least square problem into this Rx minus Q transpose B, and then the situation becomes much simpler, okay? Because we can just utilize this back substitution. And also the point is that the solution that minimizes this x over here, which is the solution of this upper triangular kind of matrix type of a linear system, and that solution will be the same as the solution that minimizes this original solution. Okay, so in this case, yeah, back to this householder stuff. So given this matrix A that we want to change into our matrix R, which is our upper triangular matrix, right? And also, yeah, changing from this guy into this, we need R, right? And also we need Q transpose B, right? So here it seems that we need a Q explicitly, but it turns out, yeah, not to be the case, because, yeah, we start from like matrix A to apply this QR decomposition to make our matrix R, right? And also we have this vector B in the case of least squares, right? So in this case, let's just imagine like applying the householder reflection like iteratively following this process. In this case, yeah, we simply follow this path, right? And then over here, this part, okay, the last line is the result of applying, for example, QK onto the intermediate output, right? So for example, if we have like over here, and then we have a full matrix, and then we will apply Q2 to introduce the zero structure over here, right? So this Q2, just like how we apply this Q2 into this matrix to introduce the zero structure over here, and then this vector, original vector B will just follow by just multiplying this Q. So for example, it's A and Q1 and Q2 and maybe Qn, for example. So this is all the sequence of the sequence of orthogonal matrix that we apply, right? So here the main point is that we don't actually need to explicitly form that part, right? And that's what I'm currently trying to explain. And in this case, because this is an entire Q, and so we just additionally compute the multiplication with the Q1 with B and Q2 with B and Q3 with the intermediate result starting from the B, right? So in this case, Q1 is just the entire F, and so we compute the multiplication with B, and then in general, this guy will have just a fully non-zero vectors, right? And then this Q2 is now the embedded one, like this, right? And so we know that when multiplying I with the upper part, it will not change, right? So in this case, yeah, we just need to multiply this F with this part, and so we update that lower part, right? And then in the next iteration, yeah, although yeah, we need to embed this f like into this smaller region. I mean, one dimension smaller sub block, but in that case, multiplying this f with this, and then we now multiply that f with the one smaller kind of vector, right? So that way we can obtain this Q transpose B, right, by just following this sequence of this Hausholder like orthogonalization, right? So in this process, we only need to add one more line to just keep updating our vector B. Okay. So that way, yeah, we don't actually need to explicitly obtain the Q. I mean, what's exactly the meaning of obtaining explicit Q? So when obtaining Q, we actually need to compute this like F1, like bigger one, and this is Q1, and Q2 will be so 1 here and 0 here, 0 here, and F2 and 1, 1. Right? So we need to compute this whole product of these matrices, right? So that's how we can obtain the final matrix Q. But yeah, in this Hausholder based orthogonalization, we didn't actually explicitly form this product of these whole matrices, right? So the point, point is, oftentimes we don't actually need to obtain this explicit Q, so we actually avoid this kind of computation. Okay, so we only compute R, and also we only compute Q transpose B, just the following, or keep multiplying this lower and lower part of our matrices or vectors. So that is the that's the idea of this implicit calculation of Q transpose B or Q and X. And so yeah. Any questions so far? Okay, so here so we see two different pseudocode that looks almost similar to each other. So in this case, what we computed is this guy, Q transpose B. For example, so we keep multiplying this Q1 through Qn on the left of the original matrix, which results in our matrix R, and we can view this part as Q transpose, and so we obtained Q transpose B, right? And then what if we just what if we have to multiply not the Q transpose B, but Q times X. Okay, so not the Q transpose, but Q. Okay, so in this case, how can we compute? So we actually follow the reverse process. So in this case, Q transpose is maybe Q3 and Q2 and Q1, and then Q will be Q1 transpose, Q2 transpose, and Q3 transpose. So when multiplying some vector B, for example, or B, okay, so in this case, we have to multiply Q3 and 2 and so on, right? And so if we imagine how we form Q1, Q2, and Q3, so they will be embedding the reflector matrix F into smaller and smaller regions on the bottom right. So when multiplying this guy with the original vector B, and then we actually simply just start from this guy, and then iteration is starting from n to the first one I, and then the remaining process is the same. So given some vector like So we apply this guy onto smaller one, and then now using the bigger one, and then we update the larger part, I mean one dimension larger size of a vector, right? So yeah, so that way once we obtain this sequence of this smaller and smaller kind of reflector matrix F, I mean sequence of F's, and then we can just multiply any vector, any given vector X or B with the original sequence or in the reversed sequence. Any questions so far? Okay, so that is the house order QR decomposition, and so yeah, let's take the break and then continue continue a little bit more on this QR decomposition using a different method. Yeah, let's start at noon.
약간 높아서 그런데 이 둘 중에 이걸 선택한 이유가 길이가 이 앵글의 차이를 고려했을 때 거의 이것보다 이게 더 비슷해서라고 하셨나요?
네.
근데 그거는 그냥 뭐 수학적으로 계산을 했을 때 그렇게 하는 거예요? 아니면 단순히 실제로 이 길이가 더 길어서 당연히 그 오차가 더 적을 수밖에 없다고 생각을 하시나요?
실제로 이 길이가 더 항상 긴지가 항상 길죠 아마?
네, 그러면
그렇죠?
긴 거는 무조건 오차가 더 적은 거라고 생각을 하고 긴 쪽으로 무조건 계산을.
그렇죠. 예. 그러니까 이게 여기서 발생이 되는 오차가 하여튼 그 지금 그 이 벡터의 랭스를 계산할 때 생기는 오차잖아요.
네.
근데 그 오차를 내는 정도가 예를 들면 10의 마이너스 뭐 소수점 뭐 16개짜리 이하를 버리기 때문에 컴퓨터가 그런 식으로 오차를 발생하는 거거든요. 그러니까 무슨 계산이든 그러니까 오차의 어떤 그게 정도는 동일하다라고 볼 수가 있어요. 10의 마이너스 16짜리 이하. 그러니까 여기서 발생되는 거 저기서 발생되는 거. 그러니까 그런 측면에서는 요 이제 매핑 되고 났을 때 거리 차이가 동일하다고 볼 수 있고. 네. 그렇게 되면 이제 각도로 보면 이제 이쪽에서의 그 각도의 오차가 더 적어질 수 있는. 네. 이 프로젝션이 약간만 틀어지면 뭔가 굉장히 긴 벡터는 이게 프로젝션 되는 값 혹은 그 리플렉션 되는 값이 또 많이 차이가 날 수가 있기 때문에 그래서 이제 예, 여보세요? 예, 혹시 제가 전화를 받았는데요. 주제가 그러니까 B가 그러니까 이게 여기서 이제 보통 이 리스코어를 푸는데 많이 활용이 되는데 그러니까 A를 이제 그 QR을 해놓으면 얘는 A를 이 어퍼 트라이앵귤러 매트릭스 그러니까 Q라는 올소고널 매트릭스를 통해서 Q를 이거를 A를 올소고널라이즈를 해서 R을 만들잖아요. 근데 이제 항상 저게 뭔가 B라고 하는 외부적으로 주어지는 저게 우리의 뭐 타겟 벡터의 그 레이블 값일 수도 있고요. 네, 그러면 이제 저 값에 우리가 그 Q 트랜스포즈를 곱한 거를 얻어야 되거든요. 여기서처럼 이런 식으로요. 그러니까 이제 뭐 이런 벡터를 저 Q 트랜스포즈라는 거랑 이렇게 곱해주는 거죠.